All right, so somebody asked me in class today why the dipole moment vector has the direction that it has, and I thought I'd just make a brief video explaining why that is the case, and I thought of a way of explaining it in a way that would make sense at this elementary level. All right, so let me just quickly recall what the dipole moment vector is. If you have two charges, q1 and q2, actually you have two equal and opposite charges, so the charges are q and negative q, and they're separated by a distance d, then the dipole moment vector p has a magnitude given by q times d. So magnitude of the either of the charges multiplied by the distance between them, and the direction of the dipole moment vector is from the negative charge to the positive charge. So the dipole moment vector points in this direction. So the question was, why does the dipole moment vector point from the negative charge to the positive charge? So that's what I'm going to explain in this video in a very elementary way. Okay, so let's first recall something from mechanics. So we had seen that suppose you've got a bunch of point masses. So M1, M2, M3, M4, and so on. Okay, there might be more. So the total mass would just be the sum of all of these, M1 plus M2 plus M3. So that would be the total mass. You can write the total mass like this if you want. All right, let's define a new vector W, which is M1 multiplied by the position vector of 1 of the first particle plus M2 multiplied by the position vector of the second particle, and so on. Now, I drew these particles as all lying in one straight line, but they don't necessarily have to lie in the same straight line. They can be in any, they can have any distribution. So the vector W is M1 R1 plus M2 R2 and so on, M3 R3 if you want. So if you want, you can also write this as Mi Ri. That's my new vector W. We don't know what it stands for, but you can see that it kind of looks familiar. Actually, you'll see why it looks familiar if you just divide the vector W by the total mass. So what does this give us? The vector W was summation Mi Ri. If you divide that by the total mass, does this quantity on the right hand side look familiar? It should. It is simply the definition of the center of mass. So this is our center of mass, right? Okay, so that is how the center of mass was defined in mechanics, right? So you take all the masses, multiply them by their position vectors, and then divide by the total mass, and you get the position of the center of mass. All right, now let's see if we can do the same thing with charges. So suppose you've got a charge q1 over here, q2 over here, q3 over here, and so on. I accidentally drew all the masses in one straight line, but there is no reason why they need to be in a straight line, because this analysis would apply in whether they're in a straight line or not. They can be distributed in 3 dimensions. So let's do exactly what we were doing with mass. Instead, we're going to do that with charge. So Q, the total charge, would be sum of all the charges, q1 plus q2 plus q3, so on. So q would simply be summation qi, right? All right, let's define a very similar vector, but instead of calling it w, we are going to call it p. So the new vector p will be defined in the same way we define the vector w in mechanics. So it would just be q1 r1 plus q2 r2 and so on. So in a compact way, you can define this as qi ri. Now this vector p is called the dipole moment of this distribution of charges. So this is a definition. It's called the dipole moment of the charge distribution. So this is the general definition of the dipole moment, right? Okay, and this is what I meant when I said in class that it's kind of analogous to the center of mass, except that instead of mass, you're using charge. Now, can we find a center of charge by just dividing, just like, can we do this third step over here? If you think about it a little bit, you'll realize that the third step does not make a lot of sense here. Why? Suppose I want to find a center of charge, right? Our center of charge. That would just be this P divided by the total charge. Can you tell me why this is not going to make a lot of sense? It is because charges can be both positive and negative, right? So the total charge could easily be zero if you have some positive charges and some negative charges. It's quite possible that the total charge would become zero. In that case, the our center of charge doesn't make much sense. So that's why we don't do this step when we have charges. So we just stick with the dipole moment. So please, so remember the dipole moment. The general definition of the dipole moment is each charge, the product of each charge multiplied by its position vector. That is the general definition of a dipole moment. Keeping this in mind, let us calculate the dipole moment of two charges. And for simplicity, let's place the charges on the x-axis, or you can place them on the y-axis. It doesn't matter. You can place the charges wherever you want. It doesn't make any difference at all. So let's place that one charge over here and the other charge over here, right? Okay. Let this charge be plus q, and let this charge, actually it really doesn't matter at all, but let this charge be minus q and this charge be plus q. All right, so we're going to apply this formula to calculate the dipole moment, right? So we're going to call this charge number 1 and we're going to call this charge number 2, right? So in order to calculate the dipole moment from this formula, I need to do q1, since I just have two charges, q1 r1 plus q2 r2. That's going to be the dipole moment. So q1 is just going to be plus q. What is r1? So r1 would be this vector. Let's say that the dipole, the distance between the two charges happens to be d. And I've placed the dipole symmetrically on the origin, right? So what is r1 going to be? r1 is going to be I hat times d divided by 2. And what is r2 going to be? r2 is going to be negative I hat times d divided by 2, right? Let's plug those in. q1 and q2 are both equal to q. Actually, the magnitudes, actually, let me just fix that. q1 is equal to plus q and q2 is equal to minus q. So all that we have to do is just plug these in. So this will be plus q times I hat d divided by 2 plus minus q times I hat minus d over 2. I just plugged in the r2, right? And so let's simplify this. This becomes I hat qd divided by 2 plus qd divided by 2. So I hat times qd, right? That is the dipole moment vector. So what is I hat times d? So I hat times d is a vector which goes from the negative charge to the positive charge, right? So you can see that you get the dipole moment for two charges. It's exactly as we discussed in class. So you can see that the dipole moment for two charges is a special case of the general formula for the dipole moment of a large number of charges. And you can kind of see the analogy between this definition of the dipole moment and the way the center of mass was defined in mechanics. Okay.